I'm Benjamin Crowell, and this is an intro to the version of a certain lab that we do at Fullerton College with magnetic fields. And we're doing it as a do-at-home lab using a kit for our students right now. So the lab is called the dipole and superposition. It's labeled Minilab 5 in my book Fields and Circuits, which you can download at lightandmatter.com. The idea here is that I have this magnet which I hung from a piece of thread off of this pencil, and if I twist it a little bit, it oscillates. And the restoring force that causes it to oscillate back through its equilibrium position is not the stiffness of the thread, it's the Earth's magnetic field, which is along this line in this room. And to convince you that that is really what's happening, it's a magnetic effect and not just the string that's twisting, I'm going to show you that it doesn't matter very much how long I make the string. So if I make the string short, like this, the oscillations are about that fast. It's about 1 per second, or a little bit slower than 1 per second. Now if I lengthen the string, this is probably a factor of 8 or 10 longer for the string. If it was the string that was causing that to come back to equilibrium, then we would expect to see a much, much longer period of oscillation. Let's see if that's the case. And I think you can see it's roughly the same. There was no drastic effect. So basically it's the Earth's magnetic field effect that we're seeing right here. So in fancy terminology, this magnet is called a magnetic dipole. That just means that it's something that has an energy that depends on its orientation in the surrounding magnetic field. And the reason the lab is called the dipole and superposition is that we're going to take the Earth's field, which is a vector pointing in a certain direction in this room, and we're going to add on top of that Earth's field vector a magnetic field coming from this electromagnet, which is a handmade coil of wire that I made. And so those should add like vectors. Superposition is a fancy word for addition. And then we should see that there's an effect on the period of oscillation that is a certain predictable mathematical form. So this video is not meant to be a substitute for your reading, doing, or analyzing lab. Theoretically, you should be able to read the lab there, use the equipment that we sent home in a kit for you, and do it on your own and figure everything out. But I think it's a little bit hard to figure out some things if you haven't seen the equipment before or don't really understand what's going on and don't have someone right there with you to help you. So this video is to help you understand what's going on. And I'm doing the lab right now with my test equipment that I bought to see if it's what we actually want to buy to send to students. So what you get might be a little bit different. Also, I'm going to distribute a somewhat modified version of that lab to my students that is adapted to the specific apparatus that we're going to be using. But the lab in the book there, it does give you the general idea. And although I'm going to read off some numerical data in this lab that I take off of my stopwatch and off of an ammeter, the idea is not for you to use my data, the idea is for you to take your own data. Now I'm going to show you a surprising problem that I ran into in this lab. It was actually kind of interesting. So I've got my magnet hanging here from a piece of thread that I tied around it, and it's the thread's about 2 inches long, and it has two modes of oscillation. There's a swinging mode and a twisting mode. So first I'm going to show you the twisting mode. This is just in the Earth's field, so the magnet is going to be oscillating around the line of the Earth's field, which is along this line, because that's north-south. So if I use this pen and start oscillating a little bit, I'm going to start my stopwatch. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I get 8.18 seconds for 10 oscillations. Now the other mode is the swinging mode, so I'm going to do that. So now it's just a pendulum responding to the Earth's gravity. It's a little bit faster. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was 5.32 seconds. So the second mode was a little bit faster than the first, but only a little bit. And the problem then is when I turn on the artificial field, that speeds up the torsional mode. It makes it about the same frequency sometimes as the pendulum mode. And then you get a mechanical resonance between those two, and they couple together in complicated ways. So I wanted to get rid of that problem because it was giving me bad data. I was getting weird patterns in my data. So I took a saw and cut this pencil off. And the idea here is this is an object that if it twists this way, it's going to have a big moment of inertia in proportion to its mass. So it should affect the torsion mode a lot and not affect the pendulum mode very much. And this is just how the method that I found in order to fix this problem, and the problem might not even occur for you. It depends on your setup. But we do want these two frequencies to be very different. So now if I measure the torsion mode, I think you can already see that it's very, very different than what it was before. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was 20.25 seconds. So now that I've done this, those two modes are no longer in resonance with each other, and you can excite one easily without coupling to the other one or exciting that one. And now I can show you that adding that piece of pencil hasn't affected the pendulum mode's frequency very much. You can see it's still quite fast. Start. Start. Stop. That was 5.3 seconds. So now those two frequencies are so different from each other that they won't couple together. And you don't have to do it the way I did it by adding something on here, although that's a pretty effective way to change one mode without changing the other. You can also change the length of the string if you need to, because that'll affect the pendulum mode's frequency without affecting the torsion mode in a magnetic field. But you want to do whatever you have to do to make sure that those two modes are at very, very different frequencies so that they won't interact. Here's my solenoid that I made for this experiment. So a solenoid is just a fancy term for a spool of wire around a cylindrical form like this. I think I made this out of a Starbucks cup. Put some duct tape around here to hold things together. Made these cardboard forms that I cut out of a file folder to keep the wire from spilling off the ends. I counted my loops carefully and I wrote down that it was 54 loops so I wouldn't forget. And then I ran the two leads out through a little hole in that piece of manila folder, duct taped them together, so now those won't cause it to unspool. And now I'm going to put my solenoid in position. I've already set things up so that the magnet is hanging at about the same height as the central axis of the solenoid. That's where the field will be strongest, so I want to get the most bang for the buck. Scooping the solenoid in there and putting it as close as I can to the magnet. I want to give the magnet a little bit of room to twist, but I want to get close so that I get a nice strong field at the position where the magnet is. And I just was looking around for some non-magnetic weights that would be strong, heavy enough to hold this thing in place. So I found these two ink jars that I had sitting around. And so now I've positioned everything so that there's about an inch between the magnet and the solenoid. Now in order to power my electromagnet, I need a battery here, and it's hooked up through these wires to this resistor, which is a 10 ohm resistor. This is what's known as a series circuit. So notice how everything is just like one long chain, there are no forks in the road. It's like a big long necklace. So that's what we want. The purpose of the resistor is to limit the amount of electric current that we draw from the battery. We don't want to kill the battery by drawing a lot of current. We don't want to make the magnetic field too strong to be practical for this experiment. So that's what I'm using this 10 ohm resistor for. And I'll hold it up closer to the camera so you can see the color code on there. So if I bring it up close here, I think you can probably see that the color code on there is going from this end: brown, black, black, and then gold. Brown is a 1, black is a 0, another black is another 0. And what that means is 1 0, which is 10, times 10 to the 0. So that just means 10. So it's 10 ohms. The gold is a color code that tells you that the tolerance of the resistor is a good high tolerance resistor. I wasn't quite able to fit it on stage all at the same time, but I also did hook in this meter in the circuit. This is an optional part of the circuit, but it's kind of helpful so you can check what's going on. So I'm using this to measure electric current, which is sort of a measure of how much electric charge is flowing through here. Because these are metal wires, that charge is electrons flowing. I've got the rotary dial pointing on an amps scale over here in white at the 10. That's a scale that lets you read a maximum current of 10 amps. I've got one plug in here in the common, because you always use the common plug, that's why it's called common. And then because I'm on a scale meant to measure large amounts of current, up to 10 amps on this scale, I have it plugged in this plug that says 10 amps DC, not in the one that says milliamps, which wouldn't be able to handle this amount of current. I've got my circuit unhooked right now so that no current is actually flowing. But if I go ahead and complete the circuit, you should be able to see it give a reading. And now it's reading about 0.14 or 0.15 amps of current. So I would read that as 0.145 or something for my data. And so that's a measure of how much current is going through the coil, and that tells you a measure of how strong the magnetic field that the coil creates is going to be. And by the way, this whole thing is still hooked up in series, okay? So this going through here, going through the battery, resistor, and the magnet, it's all one big chain necklace. It's a series circuit. So if you recall before, with the extra piece of pencil on here, I got a period of about 20 seconds, or actually 1/10 of that, 20 seconds for 10 oscillations, when there was no magnetic field turned on. But now I've got the magnetic field turned on from the solenoid, so now I'm going to see if that's changed the period of the torsion mode of this pendulum. So if I tweak it over a little bit like that and then let go, it seems faster. I'm going to measure that. Start 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that was 14.89 seconds, and so it did shorten the period of the pendulum. That tells me that the magnet's field, the electromagnet's field, is in the same direction as the Earth's field, and it's helping to provide a restoring force. Now I'm going to try reversing the field. So you can see I've still got 0.15 amps of current. And remember, I've got the black wire up here and the red wire down here from the battery. I'm going to go ahead and unhook those. Swap this around. So now the battery is like a pump, and it's going to be pumping current through the circuit in the opposite direction. And notice how there's a minus sign on the meter now. So that verifies that I've got about the same amount of current, but going in the opposite direction now. So now I think what's going on is that the current through this solenoid is creating a field that's in the opposite direction compared to the Earth's. That should make a magnetic field that is smaller than either the Earth's or the solenoids, because they're fighting against each other. And I would expect a long period for this. So I'm going to go ahead and test this. go ahead and kick this just a little bit. Start. 1, 2, it's clearly very long. 3, 4, 5. I got impatient and stopped after 5 oscillations instead of 10. That took 21.1 seconds, so the period has about doubled, and that makes sense because the field is so much weaker. Now I'm going to try to get more current. So you can see right now it's 0.14 amps of current with this resistor. I'm going to take the resistor out. Oh, it's hot. So that heat was because there was a fair amount of current going through this resistor. That's probably good for you to know. And now, let's see if it's okay to touch. Seems okay now. So I'm going to take it out. And I have a second identical 10 ohm resistor. And so I'm now going to twist these so that they're connected to each other and in parallel. So series would be like this, but I'm going to do them in parallel like this. Those two resistances in parallel are now equivalent to half the resistance. So it's twice as easy for the current to get through because it has two different ways to go. So for the same 1.5 volts from the battery, I'm expecting to get twice the current, or roughly 0.3 amps. Let's see if that actually happens. And I do get roughly that, right? About 0.28 amps. That was plus 0.28 amps, the way I have the meter hooked up, which I figured out means that the solenoid's field is helping the Earth's field, and therefore we expect the period of the pendulum to get even shorter. So I'm going to go ahead and measure that. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And that was 12.84 seconds. That was the shortest period I've had so far, so that makes sense.